Everybody, can you see my screen?
Yeah.
Yes, I can see it.
Okay, great. You see, until last class, we are looking the working principle of synchronous motor, and then we covered these things. At last, we are discussing the role of damper winding in case of synchronous motor and in case of synchronous generator. And we found out that for synchronous motor, damper winding is needed to initially start the motor. And for synchronous generator, that damper winding can eliminate the hunting effect. We covered up to that. Now moving forward, today we will be looking, effect of excitation on power factor. So you remember that in case of synchronous generator, through the vector diagram, we concluded that when the power factor was lagging, it was over-excitation case. And when the power factor was leading, it was under-excitation. And for unity power factor, it is normal excitation. But on top, we will be discussing with the help of phasor diagram that when it is leading power factor, then it is over-excitation. You see, exactly like opposite conclusion, like very confusing. See, the for synchronous generator, in case of lagging power factor, it is over-excitation. But for motor, during leading power factor, it is over-excitation. And then again, the same thing goes for lagging power factor, it is under excitation. While for synchronous generator, it was for the leading power factor under excitation. So for unity power factor case is the same conclusion. So therefore, you might be asked this question, okay, explain the impact of excitation on power factor. Then exactly you have to write these things. But don't swipe the result. I mean, don't say that this is the motor and then this is the generator. Then completely it will be wrong. So therefore, this is very confusing, but still you have to remember this thing. So now I am going to explain that in case of synchronous motor, why we get this conclusion, like for leading power factor over lagging power factor under excitation and unity power factor normal excitation. So therefore, let's take you to that whiteboard. Then you will be getting that. Uh, hold on. Okay. So first of all, then let me draw that diagram that we used in case of the synchronous generator. Like this was your EA, and you see. So therefore, this is terminal voltage, and this was we call the internal generated voltage, and this was your the direction of current, and this was the RA, and this was XS, synchronous reactance. So if you remember the synchronous generator equivalent circuit, then this was the equivalent circuit for synchronous generator. And then everybody look, the current direction was here, I mean towards the terminal. So this was the internal voltage, but there was some drop IARA plus JIAXS, and this was the terminal voltage, which would be available to the customers or to the grid. So now everybody see, today because I will be discussing the synchronous motor. So motor means the current flow direction will be from this side to this side. So this will be your direction of current, not this one. So that's why I will eliminate this thing. So therefore this will be your direction of current. So that is the motor. And then definitely you see that in case of the generator, initially this voltage was built up. This was the internal voltage. And then after deducting the drop, we got the terminal voltage. But today, when I am discussing about the motor, this is the first voltage. VT voltage is applied across the terminal. And then later this voltage is being developed This is called the back voltage. Back voltage, I am coming that point. So I mean, easily you can understand that this is your applied voltage and this is the motor. So motor is not generating any voltage. So once the motor has started rotating, then it will build up on voltage on the armature coils or stator coils, which is internal generated voltage. But actually you will be applying this voltage and this is your current direction. So therefore, based on this diagram, and if this is the current flow direction, so what will be the equation for this one? So equation will be, you can say that your EA, that one is, so VT, terminal voltage, and then I will give minus sign. So IA, then in parenthesis, RA plus JXS. Sorry, RA plus JXS. So if you remember the generator equation, then in case of the generator, it was plus sign. So this is the main voltage, and then this is the terminal, and you add it up all the drops. But today, because this is my main voltage, VT, so from there I am subtracting this. Then I am getting this voltage. And this is the internal generated voltage. So I am coming that point later. So from there, I would write down just one equation. For example, what will be your IA? So therefore, everybody see from this on, so IA would be your VT minus EA, then over RA plus JXS. This will be your IA equation. So therefore, according to the IA equation, you see, there is two voltage. One is that applied voltage, which, and then there is the minus sign this one. So this means the current value is dependent on this factor in the numerator. This is your fixed RA plus JXS. It is whatever is available in the circuit. But you see, IA value is dependent on this one. And then you see that VT is your applied voltage. This is also your some sort of constant, you can say. But the IA is dependent mainly on the EA, internal developed voltage in the motor. This is not the applied voltage. This is the internal developed voltage. And when it is developed, so therefore, for example, if I briefly explain you, this is the motor shaft. Keep in mind that this is not the generator, this is the motor. So, and then I'm assuming that motor has started rotating and it has that north pole and the south pole. And because this is motor, so you are applying the voltage or the three-phase current. So, just a moment. Okay, so because this is motor, so you are applying three-phase voltage, and then what is happening? We discussed that there will be rotating magnetic field, which is that phi s, and then we explained that later with the help of the damper winding, this motor will start rotating. So now everybody see, assume that shaft has started rotating. So when that shaft is rotating and a physical north pole and south pole are placed on the rotor body, but these coils are static. So therefore, when the motor is running, there will be one voltage build up on these coils. So that for phase A, this is that voltage, internal developed voltage. But what it will do, it will try to oppose the main voltage. For example, here you applied the voltage VA, here it is VB, and here it is VC. So this internal generated voltage will start opposing the main applied voltage. That's why you are looking the minus sign here. So therefore, what is that one? What is that rule? That is called the Lenz law. That is called the Lenz law. Lenz law. Can you remember from the physics Lenz law? L E and then Z apostrophe Lenz law. So according to Lenz law, it will oppose the main voltage. That is its characteristics. I mean, EA became developed, EA got generated because of the application of voltage. But once it generated, then it starts opposing the main voltage, which is called the Lenz law. So that is the meaning here. So this means that EA is coming only when the motor has started rotating. If motor does not rotate, then there is no EI. So this is called the back voltage. So you will be remembering this term. This is called the back voltage. Because it opposes the main voltage, that's why it is called the back voltage or sometimes back EMF, electromotive force. Now, as I said, that this voltage is developed because of the rotation and there is magnetic field. So definitely that EA, you can say that EA is the function of, EA is the function of that flux. How much flux is on this North Pole and South Pole, and what is the speed of rotation. So therefore, this EA is dependent on two factors. If you increase the flux, then the EA will increase. If you decrease, then that will decrease. So why I am saying this one? Because amount of IA or the magnitude of IA is dependent on this factor. Your terminal voltage is the applied voltage, which is available on the system or along the line. But this is dependent on the amount of flux and then the speed of rotation. So if you say that speed of rotation is fixed, synchronous speed, then the only factor which is the phi. Therefore, depending on the phi, EA can be 0. So therefore, at the very beginning, everybody say, when you are applying the voltage or the current to the stator coils, initially EA is 0. And once the motor has started rotating, only then the voltage will build up along these coils. Then gradually it will start producing. It may happen that it might be equal to Vt. At that time, I could be 0, or even it could be much greater than. So in that case, that will be the leading power factor. So I am coming those points on. But at this point, so everybody understand these interactions and these I equation, this EA equation for motor, that's back voltage and this equivalent circuit. And then now with the help of this equation, I will try to explain you if it is lagging power factor, then what? If it is leading power factor, then what? And if it is unity power factor, then what? Everybody, could you follow me what I am saying?
Yep.
Okay, fine. So therefore now, so I already saved, and then again what I am doing, still I will be on this page. I am deleting these pictures. We don't need this one. Um, Even I am deleting these pictures, only I will be keeping these two equations in front of you. Then you will be able to understand. Okay. Now everybody see, with the help of this equation, I will be drawing the vector diagram. So therefore, first assume that it is the lagging power factor, for example. It is the case of the lagging power factor. So how can you draw the vector diagram? So the vector diagram will be, let's say start, for example, my reference is Vt. That is my reference. And then because I am assuming lagging power factor, definitely, for example, this is my I. So this is that power factor angle and it is lagging. Now look this equation. I want to reach EI. So I have to consider this one. So everybody look, if it would be plus IA here, then what I would do? IARA, I would draw the IARA here, right? I would draw the IARA here, parallel to the line. This would be the IARA. But because there is minus sign, so I have to go in the opposite way. This will be my IA into RA. Everybody, could you follow me? So therefore ultimately I will eliminate this line. I will eliminate this line. So what I am saying, if you remember the generator case, there was plus sign here for generator. But because we are discussing the motor, that's why we got the minus sign. So now at first I drew that VT and IA because lagging power factor, and then I have to take into account these two voltage drop, minus IARA and minus IAJXS. That thing I am telling, that because this is the IA direction, so if it would be plus, then how would you plot IARA? Definitely parallel to this one, it would be here. But instead of going downside, I went the opposite side because of the minus sign. And then assume that it is plus sign. If it would be plus sign, then what would be JIAXS? Then definitely, JIAXS would be here. I mean 90 degree of the IA, the JIAXS. But that is the inductive voltage drop. In case of inductance, voltage lead current by 90 degree. So I should go in that direction. But now instead of going in that direction, from here, parallel to that line, I will be coming downward. So that will be mine, that minus IA JXS. So this is my, in fact, J IA into XS. So then, I will ultimately delete this line. So therefore, finally what I am getting, this is my final vector, which is this EI. So I got the EI. And then angle between VT and EI, which is called the delta power angle. So therefore, everybody say, I got this vector diagram when I consider the lagging power factor. But just by looking, although I drew by my hand, but by just looking the projection, what you guess? In this case, you see, like EA is much less than the VT. EA is much less than the VT. We got that conclusion. Because if this is the length of VT, then this is the length of the EA. I mean, this is not perfect as I drew by hand, but still in real practice, you will get this conclusion. So meaning that, what is the EA? EA is the internal generated voltage or the back voltage. And what is the governing factor of this one? Two factor. One is the phi and then the omega. Like few minutes back, I discussed you. So meaning that because EA is much less than VT, you need less excitation during lagging power factor. That's why the conclusion in this case, this is the under excitation. Sorry. This is the case of the under excitation because you need the less amount of flux to produce this amount of internal voltage. But you remember, in case of synchronous generator, we got the opposite conclusion. So our conclusion was that EA will be greater than the VT. It was overexcited case, but we got the under excitation. Everybody, could you follow this diagram?
Yeah, sure can.
Yes, yes. So you just go back to your circuit, I mean the phasor diagram chapter. Exactly, we are drawing the phasor. Okay, so we got this conclusion. Now I like to draw another one, the leading power factor. So if it would be the leading power factor, let me draw it here. If it would be the leading power factor, so how you can draw that one? Sorry. Let's say this is your VT. And if it is leading power factor, then definitely this is the direction of the IA to indicate the leading power factor. Now come back here. Now look this equation. I have to plot minus IRA. Therefore, everybody see, if it would be plus IRA, then I would put parallel to that ILN, I would put IARA here, this line. But instead of going that side, I will go in the opposite side. I will go in the opposite side. So this is now my IA into RA. Sorry, this is my IA array. So definitely I will omit that one. And then see, again, it would be the plus I, if it would be the plus sign here, then where I would put that vector, this one, JIA axis, definitely 90° ahead of IA. So it would go 90° in that direction. So, but instead of going that side, I will be going the opposite to that here. This means parallel to that. I will be going this side. This will be my JIA axis. This is my JIA into axis. So therefore, let me first eliminate that thing. Oh, sorry, that was the IA. This is the IA. So therefore, what is my final vector? Everybody see, this is my final vector at this point. Now this is my EA. So therefore, just by looking the projection, you can guess that in that case, EA is greater than VT. EA will be greater than VT. So meaning that how you can increase the EA? Because EA is the function of flux and the speed of rotation, it should be overexcited. Therefore, when it is overexcited, this means that is the case of the leading power factor. So therefore, we can write here conclusion that for leading power factor, it is the overexcitation. It is the overexcitation during leading power factor. Everybody, could you follow me? This one?
Yes. Is there also a delta for the overexcitation as well?
Yeah, of course. The angle between VT and in each case, right? So just a moment. Of course, in each case there is delta. So angle between VT and EA is called the delta. And angle between VT and IA is called the theta. This theta is the power factor angle. And the angle between VT, that is the power angle or the torque angle. So yes, you're right. Okay, now everybody see the unity power factor case. Just let me eliminate this thing. Like, okay, let me eliminate this thing also. I want to draw here. Okay, so the unity power factor case. So how does it look like? Therefore, for example, this is my VT. And then because it is unity power factor case, so then definitely IA will be on the same line. There is no phase difference, theta is 0. And now everybody look, again, if it would be plus sign, then I would go in this direction to represent IA array. But instead of going that side, it will be in this direction. For example, this is your magnitude of IA into array. For example, this portion. So therefore, let eliminate this thing. And then if it would be again the plus sign, then JIA axis, it would go here in this direction, 90° ahead of that inductive voltage drop. But instead of going that side, then I will come down side. I will come down here. So this is my that IA axis. And of course, JIA axis. So therefore, let me eliminate. So what is my final vector? This is my final vector. So this is now my EA. So therefore, in this case, you see that resistance is pretty negligible in case of synchronous generator motor, very small value. So therefore, this drop is not that much. So VT and EA will be like pretty much close. They will be very close, nearby. They will be pretty much close. So that's why in this case, unity power factor case, it is called the normal excitation. It is called the normal excitation for the unity power factor case. For the unity power factor case. Because you need some moderate, the good amount of excitation. It is not under excitation nor over excitation, normal excitation. So that's why in case of the motor, we got this conclusion. But in case of the synchronous generator, we got the opposite result. Unity power factor case was the same, but this was just the opposite, just the reverse. We got overexcitation during lagging. And in case of the uh, lagging power factor, in case of leading power factor, we got the under excitation. But today we got the opposite result. So is everybody fine? Could you follow me fully?
Yeah, sure can.
Oh, okay, great. So therefore now I am stop sharing. I'm taking you back there. Yes. Now see, so this is the conclusion that I have written. So that definitely you will be asked this question in the upcoming midterm exam or even in the final exam. And then, as I said, don't mix up these two. You see, very confusing, very confusing. Therefore, if you get confused during the exam, then try to draw the vector diagram. Then you will get the, the accurate result, correct result. So therefore, in the next slide, you see, these are the things I was drawing. So if you see the book, in the book, it is, I think, currently we are in chapter 7 of the book that I am following. This is figure number 7.12. You see, this is the case of unity power factor. The last one I showed you. The middle one is the leading power factor case. You see, this is the EA vector, and this is the terminal voltage. So EA is much larger than this one. And the third case, this is the under-excited case. You see, this is your terminal voltage, but then this is your internal or the back voltage, which is much less. So therefore, you look those diagrams that I drew, these things, and then you try to remember these conclusions. Okay, so now moving forward, there is two curves which is very important for synchronous motor. One thing is called the V curve. It looks like the letter V. Accordingly, it is called V curve. What is that? The field current versus armature current curve. So again, I will take you to the whiteboard, then you will understand. So the relationship between armature current or stator current versus the field current. It will look like, if I plot it, it will look like the letter V. Accordingly, it is called V curve. Pretty interesting. I mean, if you increase the field current or decrease the field current, I mean, under excitation, over excitation, normal excitation, depending on that, armature current will change. That curve represents the V curve. And then inverted V curve, again, if you plot that field current versus the power factor, which is called inverted V. This means this is the letter V, but it will be inverted V. So therefore, let's have a look at what is that V curve and inverted V curve. So I will take you to the whiteboard once again. Okay, so again, I will be eliminating these things, but I will only keep the equation IA. Okay, just I will be keeping the IA equation, then you will be understanding. Okay, this is my IA equation. And as I said, that EA is the function of flux phi. And of course, it is the function of the omega. But because this is synchronous motor, so speed is constant, speed is fixed. So the main factor is the flux or the field current. So now I am plotting, you see, I am plotting that field current to represent this flux. This is your field current actually. And then here it is armature current, this one. So therefore, everybody see what I said, EA is the back voltage, internal generated voltage, but back voltage. At the very first operation, at the very first moment, EA is 0. There is no EA. So therefore, at the very beginning, So therefore, if EA is 0 at the very beginning, when the motor has not started or the back voltage has not built up, at that time, what is the value of I? I is Vt over this one. So this is your, the fixed thing. This is the synchronous impedance GS. So only change is here. So you are getting the highest current because I equal to Vt over this one. So this means, you see, you will be getting very high value. For example, around this amount. And then motor has started rotating. Everybody say motor has started rotating, meaning that back voltage has started build up. So gradually this value is increasing with the increase of the flux. So meaning that what is happening? Because it is subtracting, so your I value is decreasing. So everybody see, in this axis your field current is increasing. This means A is increasing, but gradually your IA is decreasing. For example, next time this point, next time this point, and then with the increase of the flux, what is happening? At some point, Vt will be equal to EA, meaning that your IA will be 0. That's why at some point it will be 0. And then again, what will happen? Still you are exciting. You are putting much more field current or the flux. So what will happen? You will getting increase, and then it is going the overexcitation mode. So overexcitation mode means you are going the leading power factor zone. So when you was pretty much low, and then gradually you are increasing, meaning that from the lagging power factor, you are going to the leading power zone. At this point, it is 0, but then again, you see, in the reverse direction, it is increasing. So therefore, this looks like the letter V. Accordingly, it is called the V curve. This is called the V curve. So therefore, this is the 0 when Vt equal to EA. So therefore, everybody see, so the left side is for the lagging power factor. This side is the lagging. And then the right side is your, right side is your leading. And this point, when current is 0, this is the unity power factor zone. Thus, this point, this is the unity power factor. At this point, it is the unity power factor. This means that is the thing we learned few minutes back. When Vt is almost equal to EA or exactly equal, that time current is 0. This is that point. So when Vt equals to EA, what conclusion we got few minutes ago? That was the unity power factor, normal excitation. When EA is very, very low, meaning that is the effect of under excitation, that is the left side. At that side, current is highest when it was EA 0, and then gradually increasing. It is increasing, but that is the lagging power factor zone. When current is fully 0, Vt equals to EA, that is the unity power factor. And again, in this side, that is the leading power factor. Now, if I plot just at the bottom, you see, based on that conclusion, if I plot here again that field current versus the power factor, I am plotting the power factor. So therefore, if I do point by point, actually it will look like this. It will look like this. Like this point is corresponding to this point, and like I am plotting each point. For example, this point is here, this point is here, this point is here. So accordingly, this is your unity power factor line. I mean this one, and then the left side is your lagging, right side is your leading. Because you see that I got the highest current. When you are getting the highest current, meaning that the EA is almost 0 or the 0, and then gradually you are increasing EA. So meaning that is the under excitation. EA is very, very low, means that is the under excitation. And what conclusion we got several minutes back? Under excitation means lagging power factor. That's why this is your like power factor 1 position, and then gradually, for example, this is just an example 0.2, this is 0.6, this point, sorry, this point is 0.8, and then finally here it is 1 power factor at this point. So therefore, again, from this point, your left side is lagging power factor, right side is leading power factor. So, but you see, it looked like the letter V. Accordingly, it is called the, therefore, let me remove these lines. Yes. So therefore, because this looks like the inverted V, letter inversion of V, accordingly, it is called inverted V curve. So it is called inverted. It is inverted V curve. So this is V curve inverted. So therefore, it is easy to remember, you see, in both cases, the x-axis, horizontal axis is the field current or the flux, IF. In case of V curve, y-axis, vertical axis is this IA, armature current. And for inverted V curve, vertical axis is your power factor. So therefore, this is very, very important. Sometimes in like power industry, you are being interviewed for job. Very frequently, they ask this question: that do you understand or do you know the meaning of V curve, inverted V curve? So therefore, answer would be yes, I do know. So the IA versus IF curve is called V curve, and power factor versus field current curve is called the inverted V curve. Everybody, could you follow me?
Yes, I can. Yeah, I can.
Yeah. Okay.
Yeah.
Yeah. Good. Even like at the end of the the semester, because you will face on, I think, a final quiz for the lab, it is highly likely that the lab TH will ask you this question. They will tell you to draw the field current versus this one and field current versus the power factor. Or they may tell you, okay, draw the V curve, inverted V curve. Because like your experiment number 5 and 6 will be about the synchronous machine that time. So they might ask you, or if not, and then at the end of the semester during final quiz, frequently they ask these questions. Okay, so then moving forward, there is another, I think, interesting thing. So we covered this thing. You look this up, synchronous condenser. So we are studying the synchronous motor, but synchronous motor is also called synchronous condenser under a certain condition. So synchronous condenser means synchronous capacitor. This means that synchronous motor can fully work as a capacitor. So what is the condition? If a synchronous motor operates in overexcited mode and it has almost no mechanical load connected, then it behaves as a capacitor. And under such condition, the motor is called synchronous condenser. And because I am showing you one vector diagram, then you will get it. Because it behaves as a capacitor, pretty interesting, that synchronous motor can work as a capacitor. Pretty interesting. Because it can work as a capacitor, what is its main role? Its main role is to improve the power factor. That's why in real world practice, it is connected in parallel with the induction motor load to improve the power factor. Because you know that when we started the induction machine, you notice that power factor was always lagging, because induction machine always draws the reactive power from the system, both in motor mode and generator mode. That's why power factor is always lagging in case of induction motor. So that's why, to improve the power factor of the induction motor, this synchronous motor is connected in parallel. Therefore, instead of connecting a capacitor, simply you can connect a synchronous motor. It will work the same way as the capacitor. So this means that you all know the property of capacitor. In case of capacitor, current leads voltage by 90 degree. So exactly same thing will happen for a synchronous condenser, current will lead voltage by 90 degree. You see that I was showing you those diagram VT versus I. So soon I will be showing you. And then you will be noticing that, pretty interesting, that delta angle, power angle will be almost zero. And that is the meaning that it has no mechanical load. So therefore, when I are getting this conclusion, when the synchronous motor is running in overexcited mode. So what is the meaning of overexcited mode? Meaning that that EA is much greater than VT, and it is the leading power factor case. Just we drew the conclusion few minutes back. And it has almost no mechanical load. Under that condition, it behaves as a capacitor. So that's why, to understand that, let's have a look at the board once again. Then you will get fun. Okay, everybody, let me okay, so for example, you assume that this is your VT, terminal voltage, and you assume that this is your IA. Because it is overexcited, and I am assuming that IA is fully 90 degree leading. The way capacitor work, I started with that concept. This is VT, but this is I. It is the theta is 90 degree, fully leading. Now, you see, now I want to plot those things. I mean, basically that equation. Although I removed that equation that EA equal to VT minus IRA, but it is the same thing. So if it would be generator, then IARA would go in that direction, upper direction, parallel to that one. But I have to come downward. For example, this is my IA into RA. And then if it would be again generator, then I would go in that direction. I mean 90 degree ahead of that to represent that JIA excess drop. But now instead of going there, I will from here, I will be going in that direction. For example, this is my JIA into excess, this one. So let me eliminate this one. And then, so what is my final vector? So everybody see, this is my final vector. Sorry, this one. So this one is your EA. This means that makes sense that it is overexcited because EA will be much greater than the VT. And can you see the delta? Although I drew by hand, there can be very small angle, sorry, there can be very small angle delta, but that delta will be like pretty close to 0 degree. There can be 1 degree or 2 degree in real practice, you see, because I am drawing by hand. But at least you can understand that it will not be much. The cases that I discussed few minutes back, your delta will be very close to 0. That is the meaning of the mechanical load. So that's why under this situation, that motor will start working as a capacitor. Because you see, I started in that way. This is fully like this theta is 90 degree. So this condition is called that synchronous condenser. Therefore, if you remember the equation, let you to that PowerPoint file again. If you all remember, you see, once I showed this slide. Can you remember? The previous class I showed you this slide. I think in case of generator, this is the power equation. So there will everybody look the power equation. If delta is very close to 0, then what will be the power value? It will be 0. But you look, this is the Q equation, reactive power. When the delta is 0, definitely you have the Q value. So therefore, this means when delta is 0, your active power is 0, but then you have the reactive power. So therefore, what is the property? Which element can provide that property that power will be 0, active power will be 0, but there will be reactive power? That is only that capacitor. This is the condition. So therefore, the equations also make sense that the delta should be 0, almost 0, or close to 0. That is the meaning of this one. Therefore, everybody once again look, if a synchronous motor operates in overexcited mode and it has almost no mechanical load, meaning that delta is 0, then it behaves as a capacitor. Everybody, could you follow me?
Yes, I could. Yes.
Yeah. So therefore, now everybody see, as I said that this is equivalent to capacitor. Now you see the homework set 3, problem number 5, the last problem. You are assigned a homework, last problem. It is about the power factor improvement. So therefore, the way you use the power factor improvement concept with the help of capacitor, exactly it is the same concept, exactly the same thing. You remember that we use power triangle, the what is the old value of theta, what is the new value of theta, what is the old power factor, new power factor. Exactly, you have to use the same concept to solve the problem number 5 of the homework set 3. So that is about the synchronous condenser. So if you now see, everybody see your homework set 3, the last problem, that is about synchronous condenser. So therefore, at the first chapter, three-phase circuit chapter, you see, we solve few problems about power factor improvement. Exactly the same method you have to use. Just it is the synchronous motor. So only thing that you have to find out what is the active power, what is the input power to the motor to solve that problem. And then the rest of the procedure is the same, power factor improvement. So therefore, again, this is pretty interesting, and then this is very important. Again, many times, for example, you're hearing, you're listening someone's lecture in some conferences, in some symposium, and then they might talk about synchronous condenser. So therefore, basically synchronous condenser is nothing but the synchronous motor under a special situation. What is the special situation? It should be running in overexcited mode, and also it should have no mechanical load connected. Under that situation, it will work as a capacitor. So then accordingly, I may also ask you in the upcoming midterm exam or final exam, what is the condition that a synchronous motor will behave as a capacitor? That time exactly you have to write this thing. And what is the application? Application is that it is connected in parallel to the induction motor. This induction motor, mostly the industrial load, huge size of induction motor. Now you might argue that why I will be connecting the synchronous condenser because it is rotating. But if you can use the simple capacitor, no problem, in parallel to the induction motor, but the size will be huge. It will be very bulky, very large size of capacitor. And it might be more costlier than even the synchronous motor. That's why industry prefer to connect the synchronous motor, the synchronous condenser, to improve the power factor. So therefore application is there. Okay, so I think everybody understood. And then now moving forward, I think today I have set up some questions so that you all can participate. And then you will be done for today. Everybody see there is some setup question for the synchronous motor and synchronous generator. So the first question everybody see, what will happen if you connect a 60 Hertz device to a 50 Hertz system? The meaning that, for example, you have a device or whatever it is 60 Hertz, but you are connecting to a system that has 50 Hertz. So then what will happen?
The device you plugged in will be damaged, or could technically hurt the wiring in the building too.
Yes, yes. So therefore, you see, we were discussing, I think, previous class, the synchronization procedure. we noticed that there were 4 conditions, like their voltage must be the same, and their phase sequence should be the same, phase angle should be the same, even frequency should be the same. And then if any of the conditions do not meet, then there will be circulating current flow. So meaning that, for example, you have a device, a hair dryer, and then you went foreign country like Europe, they have the 50 hertz, and you are staying in hotel, and then you plugged in your device. You did not, I mean, before going, you did not take care, you did not buy an international device, you just plugged in your hair dryer there. So they have the different frequency. Your frequency, your device 60, but their system is 50. So what will happen? There will be circulating current flow. There will be circulating current flow. And that circulating current flow will cause loss. And then, as you already mentioned, it may be burnt up, or it will be damaged. Or even though may not be fully damaged, but it will be overheated. That is the impact. So that's why, I mean, never ever connect. Same thing when the European people come here in the North America, they should be careful. If they bring their hair dryer or something in the hotel, then they should be careful, or the charger or any device. Same thing, the voltage issue. What will happen if you connect a 120 volt device to a 220 volt system? The same conclusion. There will be circulating current flow. Consequently, your device might be damaged. I mean, immediately it might not be burnt up, but over the time, if you really feel, if you touch the wire, connecting wire, they will gradually heat it up, at some point. It will be burnt. Okay, so the question number 2, everybody see, how does a synchronous machine differ from an induction machine? Now, I mean, today we learned synchronous motor, and then 2 classes back we learned synchronous generator. Both synchronous generator, synchronous motor, I am telling the synchronous machine. When the word is machine, meaning that it could be motor, it could be generator. I mean, it could be both. Same thing, induction machine means it could be induction motor, it could be induction generator. I mean, both. So the context of the question, how can you distinguish a synchronous machine with the induction machine? So what you've noticed, like last 3-4 classes we are discussing synchronous machine, motor and generator, and then several classes back we discussed induction motor, induction generator. So what is the difference? How would you answer to this question? Alexandria, can you mention one point?
You said to answer that question?
Yeah, what I mean, there can be several points. Just can you mention one point at least? How would you distinguish the induction machine and synchronous machine? For example, just how about the speed, in terms of speed?
This
Yes, please go ahead.
you're asking me like to differ between the induction motor speed and the synchronous?
Synchronous motor speed. So in terms of speed, is there any difference? So what is the meaning of the word like synchronous? I mean, why are you calling this synchronous machine? What is the meaning of the word synchronous? Synchronous means the constant speed. Therefore, everybody listen, when it is synchronous motor or synchronous generator, meaning that speed is constant. But what we noticed in case of induction machine, was the speed constant in case of induction machine?
No.
No, yes. So, right. So that is the what I expected. That is the meaning. So therefore, first answer, there can be several points. Everybody listen. I mean, I said Alexandria, but please, this is for everybody. So you would say that in case of synchronous machine, speed is constant. It is always constant. That equation 120 F over P for both motor generator. In case of induction machine, speed can be varied. And what is the relationship? It is related to the slip. It is related to the slip. You remember? Okay. The next point, what is the slip value for synchronous machine? What is the slip for synchronous machine? So therefore, see, what is the definition of slip? Slip was synchronous speed minus rotary speed divided by synchronous speed. So therefore, everybody say in case of induction machine, synchronous speed and the rotary speed, those are not the same thing. In case of induction machine, synchronous speed was the magnetic field speed and rotary speed was actually the speed. That's why always there was difference. And that difference we called slip or the slip speed. But in case of synchronous machine, everybody see, speed is always constant. So therefore, it has the slip 0. That is the, question number 4, actually, I asked that question. Everybody say, what is the value of slip for a synchronous motor? The answer is the slip for synchronous motor is 0. Because synchronous motor has only the synchronous speed. So therefore, if you apply to the slip equation, slip is synchronous speed minus rotary speed divided by synchronous speed. For synchronous motor, synchronous generator, only one speed. So that's why the difference is 0. In fact, there is no slip. So therefore, that is the other point you can mention as a second point. First point is in case of synchronous motion, speed constant, induction machine synchronous varying. Induction machine has slip and that slip varies from 0 to 1. In case of synchronous machine, slip is 0. This is the second point. What else? Can you tell any more points? Anybody? What else? Is there any other points? So for example, was there any damper winding in induction machine? Was there any damper winding in induction machine? No, there is no damper winding. So therefore the third point will be induction machine does not have damper winding, but synchronous machine has damper winding because it is needed to initially start the motor. So and then what else? Does induction machine have any physical magnetic poles? The answer is no. So therefore other point, induction machine does not have physical magnetic poles. On the other hand, synchronous machine has physical magnetic pole. It has physical north pole, south pole, but induction machine does not have. You have to create the field. Which is that? Rotating magnetic field with the application of the board. Therefore, the answer to question number 2 will be those 4 points. First you mention about the speed, then you talk about the slip, then you talk about the damper winding, and then finally you say that point, the magnetic pole. That induction machine does not have physical magnetic pole, but on the other hand, synchronous machine. Everybody, could you follow me?
Yes, yes.
Yeah. And then are you please writing down in your pieces of paper? Please you all note down those answers, because again you will be asked these questions in the midterm exam and final exam. Like this is like kind of question bank. Okay, so then moving forward, see question number 3. Why is a synchronous motor called synchronous?
Is it because it runs at the synchronous speed?
Yeah, be right. So because of the synchronous aspect, or in other words, because the synchronous meaning the constant, because it offers the constant speed, accordingly it is called the synchronous motor. Right, yes. And then question number 4, we already discussed. What is the value of slip for a synchronous motor? Slip is 0. There is no slip because there is no difference in speed. Both the synchronous speed, rotor speed is the same thing. Okay. Now question number 5, you see. Why is not a synchronous motor self-starting? Probably last class we were discussing this one. So we noticed that synchronous motor was not self-starting. So what was the reason? Can you remember? Anybody?
It was hunting, and it just means that like the motor itself doesn't have any torque to start itself.
Yeah, and then there is no torque. Plus, what is the main reason? Because it has the inertia. Rotor has inertia. Rotor has inertia. So that's why you need the help of the damper winding. You said the hunting, that is the hunting is related to synchronous generator, not the motor. I'm coming that point soon. So, but the answer would be that a synchronous motor is not self-starting due to its inertia of the rotor. The rotor has a specific mass. It has a moment of inertia. So initially, the synchronous motor cannot overcome that inertia because it does not have starting torque. That's why you need the help of the damper winding to initially produce some torque and to start the motor. And once the motor started, then it got synchronized, it got locked with the applied frequency. Accordingly, like again, question number 3, that's why it is called synchronous motor. So at the beginning, it cannot self-start, but once it takes the help of damper winding, then it gains, then it attains the required starting torque, and once it is started, then it locked with the synchronous speed. Everybody, could you follow me?
Yeah, makes sense.
Okay, great. So question number 6, which winding is vital for a synchronous motor starting?
It's the damper winding. We just talked
Damper
about
winding.
it.
Exactly. I mean, just a minute ago. Yes, exactly. Damper winding. And then now, I think Tyler, you are talking that hunting is related to synchronous generator. So therefore, for the synchronous generator, there is damper winding to eliminate, to remove the hunting effect. And hunting effect, as I was discussing in the previous class, hunting means due to change in load, always there is some sort of vibration or oscillation on the rotor. Therefore, to remove those oscillations, damper winding is used on the synchronous generator. But for synchronous motor, damper winding is used for starting because it is not self-starting. Now, question number 7. Why is a synchronous motor called induction start and synchronous run motor?
Well,
So
because the damper winding is an induction coil that gives it the torque, right?
yes, and yes, right. Because at the start, it is not self-starting. At the start moment, you need damper winding. At that damper winding work as the induction principle. So in other words, synchronous motor restarts following the induction principle, and later it got synchronized. With a constant speed. Accordingly, sometimes it is called induction start and synchronous run motor, meaning that it will start with the induction principle, but it will run. Running means, later, it will run as a synchronous motor. Pretty interesting. You start as an induction principle, likewise the induction motor, but then it got locked, it got synchronized at a constant speed. That's why, in this book or any other book, you will be finding this terminology: induction start, synchronous motor. instead of just the synchronous motor. Okay, and then the question number 8, is the frequency always 60 Hertz even at the steady state of a power network? Explain your answer. So we say that at the United States, we have 60 Hertz frequency. So do you think that is the frequency always 60 Hertz even at the steady state? Steady state means system is running well, system is balanced condition, it is symmetrical position, and everything is running normally. There is no short circuit, open circuit, no thundering, no lightning, nothing happened in the power network. That is the meaning of steady state. I mean, it is running as well as usual without any disturbance. So even at the steady state, so do you think that the frequency is 60 Hertz? Or it could be a little bit more, or it could be a little bit less. So therefore, to understand this on, let me take you to a whiteboard for a moment, then everybody will get. Okay, so probably you remember that in last class, I was, I think I was explaining you this equation, phi A equal to phi M minus phi A. Can you remember that I was explaining? This is called, you will be remembering, this is called swing equation. So therefore, for example, this side here you have the load or the customers. This is your generator, this is your shaft system, and this is your mechanical power here, and then it is the electrical power here. Okay. So therefore, everybody see. So therefore, my question was that question number 8, is the frequency always 60 Hertz or not? So therefore, soon you will be getting that point and you will be able to understand. This is a synchronous generator. This is its shaft. It is rotating at that certain speed. This means it has the mechanical power, phi m, which is coming from the turbine. And then this generator is producing this amount of electrical power. And here are the customers connected. Now everybody see, this is the equation which is called swing equation. What is that? Phi A equal to phi M minus phi A. And I have written that is 0. This means I am assuming that during normal condition, my phi M equal to phi A. This means that mechanical power equals to the electrical power. In other words, I am assuming that this generator has no losses, no friction loss, wind, everything. I mean, pretty ideal condition. But this is ideal condition. But now everybody see, in real practice, what is happening? Here are the loads. Customers are connected here. Therefore, continuously, this phi is getting changing. Either it is increasing or it is decreasing. Then, for example, your phi m is 100 megawatt and your phi is also 100 megawatt. And in that way, system is running well, for example. But then here we are the customers are continuously we are changing our loads. Sometimes you are turning on lights, sometimes TV or other loads, refrigerator, sometimes not, washer, laundry, etc. Continuously you are changing. You are using computer or not using computer. You are cooking or not cooking. Consequently, electrical power, everybody say electrical power is either increasing or decreasing as compared to the mechanical power. But I'm assuming that mechanical power is constant. Of course, I mean, In rare case, there can be any disturbance, any issues, but I am assuming that mechanical power is constant. There is no disturbance on the mechanical side. But because customers are connected on the electrical side, continuously you are changing. So therefore, what is happening? If you continuously change phi, will you get the zero value here? No. What result you will be getting? Either you will be getting the plus, some positive value, or you will be getting some negative value here. There will be some number here because your PM is fixed. So now, if you see that the result is positive, meaning that phi is somewhat less than PM, it is called the accelerating power. System will be accelerated. What will be accelerated? The shaft speed will go high. For example, if it is 3000 RPM, so when you get the plus value, meaning that it will go above that 3000 RPM. Just an example. On the other hand, you are putting more load on the system, meaning that it is greater than PM. So you will be in the negative value. What is the meaning of the negative? System will be decelerated. So meaning that then it might go below 3000 RPM. So, but you see, everybody, what is my synchronous speed equation? Synchronous speed is 120 F over P. Your pole number is fixed for a machine, whatever it is, either 2 pole or the 4 pole, whatever it is, the pole number is fixed. At least there are 2 pole number and that is fixed. But if the speed change because of this positive or negative value, meaning that system is getting accelerated or system is getting decelerated, which factor will affect? Frequency will affect. Therefore, you see, with the increase or the decrease of the NS, your frequency will increase or decrease. So therefore, but what is your expected frequency? Your expected frequency is 60 Hertz. And based on that, I calculated that if pole number is 2, then it will be like 3600 RPM, or 50 Hertz system, it will be 3000 RPM. That is your expectation. But you are not able to maintain 60 Hertz because continuously this rotor is vibrating and it is changing, either going little bit upward or the downward. And why that is happening? Because of the load side, because of the customers. So that was my question, that do you think that is the frequency always 60 Hertz? The answer is no. I mean, there is no short circuit, no open circuit, nothing happened. You are not noticing anything on the connected network. It looks like nothing happened. But still, if you see the frequency, it may not be exactly 60 Hertz, either a little bit higher or a little bit lower in real practice because of this thing. So now the question is, when I'm saying that, okay, you are injecting load or you are taking out load, you are controlling the fee as a customer, then what is the tolerance? So therefore the United States tolerance is plus minus 3%. Plus minus 3% of this number, of the 60 Hertz. So this means that you can calculate it can go a little bit upward or downward. If it goes more upward or if it goes much more down than this number, then that is the frequency stability, so frequency problem. And that you can understand, for example, at your home, like one of the bulb is blinking. In your kitchen area, for example, the tube light is blinking, your television screen is blinking. That can be the reason of there is huge change of frequency. Some fluctuations is going on. That is not desired. But as long as it is within plus minus 3%, that is fine. Once it goes beyond that number, then really you can understand at your home or whatever location you are. You can visualize it in terms of light blinking or some devices. The same thing. Like for example, the United States, your phase voltage is 120. So now plus minus 5%. that is the tolerance. That is the tolerance. This means that it can go upward 126 volt, 5%, and then downward it can come 114 volt. So maximum it can be 126 and then downward it is 114 volt. If it is within this zone, then it is okay. Your connected device will not be affected. Once it goes much downside and once it goes much upwards, then that is the problematic. So that's why United States had two, rules. Frequencies should be plus minus 3% and voltage should be within plus minus 5%. Then the connected device is safe. So therefore the answer, I think everybody, could you follow me what I am explaining? Is everybody fine?
Yeah, I think it's okay so far.
Yeah. So yes. So therefore now go back to that question. Yes. So now look, question number, is the frequency always 60 hertz? So answer is no. It is not perfectly 60 hertz. And then when I say explain your answer, that explanation that I showed you in the whiteboard. So you will be telling that it is not perfectly 60 hertz because customers are continuously changing the loads based on their behavior, based on their lifestyle, based on their own pattern. I am using the load now. You may not use load at that time. So different customers have different patterns. All are not the same, not simultaneous. So that's why continuously there is some sort of load change. Either someone is injecting or some taking out the load. And that impact is going on the generator, and consequently generator is impacting the frequency. I explained you everything. So just keep in mind, this is pretty interesting. And even at the steady state means system is running fine. System is running fine. Okay, now this question, what is the role of damper winding in synchronous machine? So then how would you answer this one?
Well, we've talked about them both. So for a motor, it helps start the motor, and then for the generator, it eliminates hunting.
Exactly, that is the perfect answer. So that is the meaning, like in synchronous machine, when it is synchronous machine, you have to take into account that it is telling both generator motor. Accordingly, you have to answer. So like that is the perfect answer. That for synchronous motor, damper winding is needed to initially start the motor, and for synchronous generator, damper winding is needed to eliminate hunting. Yes. Okay, the last question for today. How does the field excitation affect the power factor in synchronous machine? Then how would you answer this one? So this means that the question number 10 is exactly this one. Exactly this will be the answer. Actually, I asked this question. You see, effect of excitation on power factor on synchronous machine. Then you have to tell the both thing, that thing we learned today for synchronous motor. What is the effect of excitation? You will be telling if it is over excitation, then power factor leading, under excitation, lagging power factor, normal excitation, unity power factor. On the other hand, for synchronous generator, when it is over excitation, then lagging power factor, for under excitation, leading, and for normal excitation, it is unity power factor. Just exactly you have to tell in that way. Either you express in terms of sentences or as it is, or you can make a table like for synchronous motor, left side and then right side synchronous motor. You can use two column. Left side column will be motor or generator, then right side column will be other. Whatever way you express, this will be the answer to that question. Everybody, could you follow me? The answer to the last question. How does the field excitation affect the power factor in synchronous machine? Meaning that you have to talk both synchronous motor and synchronous generator. Okay, so with that, today I concluded that synchronous machine chapter. So from next class, I will start the DC generator and DC motor. So therefore, we are with that, like we are almost about 65%, 70% are done in the syllabus. And then the remaining about 30 or 35%, there will be DC motor, DC generator. Then we will be discussing the special machine. There are various types of motor. For example, all will be single phase motor and a special type of motor. For example, the ceiling fan, you know, what is that? Ceiling fan is a motor or a generator? What do you think? Oh, so what is the ceiling fan? Is it a motor or a generator that you use at your home?
Motor.
Motor,
Motor.
exactly, exactly. And is it three phase or single phase?
Single phase.
Single phase, exactly. So, but inside the stator of the single phase motor, inside the ceiling fan, you need a capacitor, which we did not study in case of the three phase induction motor. We studied that you need a parallel capacitor to improve the power factor. That is different thing. But in case of the induction motor, single phase induction motor that we have inside the ceiling fan in the stator circuit, you have both inductor and the capacitor. You need it as well as resistor. So that's why that single phase induction motor a little bit complicated than the three phase induction motor. I mean, that's pretty interesting. Even though it is single phase, but that working principle is complicated than the three phase. So we will be looking. And then, for example, what is the motor used in hair dryer? What is the motor used in vacuum cleaner? What is the motor used in refrigerator, dishwasher, washing machine, lawn mowing, electric saver, in computer, in electric clock, in printer. So we'll be looking like several types of dozens of types of motor, and then their working principle, and those are pretty interesting. What is the motor used in what is called VCR or the videotape recorder during printing? All will be looking. So, and then that will be the, and then at last we will be looking the transients. I mean, something similar to that swing equation that I was explaining you today. But the most of the major portions we are done, like I would say about 65% of the syllabus we are done with today. Okay, so with that, I like to conclude. Do you have any questions